Hello everyone. In this video, we're going to be talking about the spanning tree protocol. Now, when network devices want to communicate with other network devices, they first need to know the MAC address of those devices. And the way they find the MAC address of a device that they want to talk to is by broadcasting a signal out on the network asking for that device's MAC address. And then once the MAC address is known, communication can take place. So for example, if computer A wanted to communicate with another computer on this network, it'll send out a unit of data called a broadcast frame. And then once the broadcast reaches the switch will forward that broadcast to every device that's connected to it. Now, in a typical network, you would have a switch with computers connected to that switch, forming a local area network. However, in some cases, network administrators may want to add redundancy to their network in case of a switch or a cable failure. So instead of having one switch, they may use multiple switches. So for example, this network is using 3 switches on this network. So that means that this computer here has 2 options it can take to communicate with this computer over here. It can communicate using this path here, or if this link goes down, it can use this path instead, and vice versa. But the problem with having a setup like this is that it could create a problem called broadcast loops. So for example, as I stated before, whenever a computer wants to communicate with another computer, it first has to send a broadcast frame out on the network to find the computer it wants to talk to. So if computer A wants to talk to computer C, computer A will send out a broadcast frame to the switch it's connected to, which is switch 1. And remember, switches will always forward broadcasts to every device that's connected to it. So switch 1 will forward the broadcast to computer B, switch 2, and switch 3. And then when switch 2 receives the broadcast, it will forward the broadcast to computer C and computer D. But it's also going to forward it to switch 3. And then when switch 3 receives the broadcast, it'll forward the broadcast to switch 1, and switch 1 will forward the broadcast again to switch 2, and then this will continue on in a never-ending loop. And the same thing happens in the other direction. When switch 3 receives a broadcast from switch 1, it'll forward the broadcast to switch 2, and then to these computers again, and then switch 2 will forward the broadcast to switch 1, and then it's rinse and repeat. The whole network will be caught up in a never-ending loop of broadcasts, which is known as a broadcast storm. And when this happens, the network can't do anything because of the constant broadcasts, and the entire network will come to a grinding halt. So this is why the spanning tree protocol was developed. It was designed to prevent broadcast loops when multiple switches are used on a network. So the next question is, well, how does STP prevent this? Well, the short answer is that it does this by blocking certain ports on the switches. And so the next question is, how does it determine which port or ports to block? Well, the first thing that STP does is to determine which switch will be the root bridge. The root bridge will be considered the most important switch, and the way it determines this is by having all the switches talk to each other. And they do this by sending out messages called BPDUs, or Bridge Protocol Data Units, out on the network. These units contain information called the BID, or Bridge ID. The Bridge ID consists of the switch's priority number plus the VLAN number along with its MAC address. And STP uses the bridge ID to determine which switch will be the root bridge. And the switch with the lowest bridge ID value will be considered as superior and will be elected as the root bridge. So for example, by default, each switch will have a priority value of 32768. And let's say that all the switches are on VLAN 1. So we will add the 1 to the priority value, which will now equal 32769. But since all the switches on this network have the same priority value, that means it's a tie. However, the tiebreaker will be determined by the MAC address. So whichever switch has the lowest MAC address will be elected as the root bridge. So we see that switch 3 has the lowest MAC address, which means that it'll be elected as the root bridge. And the ports on the root bridge are labeled designated ports. Designated ports are ports that lead away from the root bridge. Now, the next step is to determine the root ports. The root ports are ports on the non-root switches, so these switches here, that forward data to the root bridge. Root ports are elected by what's called the lowest path cost, which means that the port on the switch that's the fastest link to the root bridge. The path cost is calculated in the following chart. If the link speed is 1 gigabits per second, the cost is equal to 4. If the link speed is 100 megabits per second, the cost is equal to 19. And if the link speed is 10 megabits per second, the cost is equal to 100. So let's say that all the links between the switches are 100 megabits per second. And if we look at our chart, 100 megabits will have a cost of 19. So all three links will have a path cost of 19. So starting with switch 1, it has two paths to the root bridge. This one here, or this longer one here. So this path here has a cost of 19. But this path here has a cost of 19 plus another 19, which equals 38. So since this path here has a lower cost, this port on this switch will be the root port. Because as I stated before, whichever port has the lowest cost path to the root bridge will be the root port. And the same thing goes with switch 2. This path has a cost of 19, and this other path has a cost of 38. So this path is lower, so this port will be the root port. Now just to give you another example, let's say that these two links here are 1 gigabits per second each. And if we look at our chart, that would give them a cost of 4 each. So going back to switch 1, if we add up the cost of this path, it would be 4 plus 4, which equals 8. And the other path is still equal to 19. So since 8 is lower than 19, this port would be the root port. So this is how root ports are determined. So let's go ahead and put these links back to 100 megabits each and continue on with the lesson. So now that we have our root ports figured out, it's time to determine which of these last two remaining ports are going to be blocked to prevent broadcast loops. And the way to determine which port will remain open and which one will be blocked is again based on the switch's bridge ID. And since the lower bridge ID wins, the port on switch 2 will remain open and be labeled a designated port. But the port on switch 1, because it has a higher bridge ID, its port will be blocked. So by blocking this port, it will shut down this link, which will prevent any broadcast loops. So STP has to go through all these steps to find out which port or ports to block. But if any of these other links or devices were to go down, STP will reactivate this port and bring this link back up. The spanning tree protocol was developed in 1985 as the IEEE 802.1d standard. And in 2001, RSTP, or Rapid Spanning Tree Protocol, was developed, which was labeled the IEEE 802.1w standard. RSTP was an improvement to STP by significantly adapting faster to a failure or to a change in the network. So where STP can take 30 to 50 seconds to adapt, RSTP can do it in under 6 seconds. And it is also backward compatible to STP. Guys, if you want to do your own little experiment, you can do this to create your own broadcast storm, just to get an idea of what happens. So you just need a standard inexpensive switch with no loop blocking features, plug in your computers into that switch, and then get a network cable and then plug both ends of the same cable into the switch and see what happens. So what's going to happen is when these computers send their broadcast frames to the switch is going to endlessly loop the broadcast. And as it does this, you will see the LED lights on the switch rapidly flashing in sync, which means that this network is in a broadcast storm, and the computers won't be able to do anything. they won't be able to exchange data between them, or if they are connected to the internet, they won't be able to access anything on the internet. So if you try to bring up a web page, nothing will happen. So this is actually a simple way to bring down a local network. But as soon as you remove the cable, everything will go back to normal. So guys, I hope you learned something from this lesson. But speaking of learning, I would like to thank the sponsor of this video, which is Brilliant. Brilliant is an online learning center where you learn by doing, with thousands of interactive lessons in math, data analysis, programming, and AI. It's a platform where you can learn different skills that are in demand today. But what makes Brilliant different is that it makes learning fun and effective, because you're not just watching a lecture or reading text, but instead you're involved in doing the exercises yourself, which makes complex ideas easy to grasp. So for example, are you interested in programming? Brilliant has a growing number of programming courses that are a great way to build foundations and learn real-world applications, such as getting familiar with Python, where you can start building programs on day one with a built-in drag-and-drop editor. You can also learn essential coding elements from loops and variables to nesting and conditionals. And you can also learn to develop your mind to think like a programmer and begin writing complex programs to build games and apps. And right now you can try everything that Brilliant has to offer for free for a full 30 days by going to brilliant.org/powercert, or click the link in the description, or just scan the QR code on the screen. And you'll also get 20% off an annual premium subscription.